Right. Good evening, everybody. We are very happy, and with we, it's a whole bunch of people, so many people that I cannot select everybody. I've just selected Lean, who will help me out if I'm screwing things up. And then we already have Laura there, who is one of the three speakers or three talks that we will have today. So it's a 35th Data Science Leuven meetup. But before I present, or I will give you an overview of the talks that we will have today, I want to bring you back to a year ago, because a year ago we were having these strange things where we would come together physically and talk about data science. It almost looks obscene now if you look at it, but that's how we used to do it more than a year ago. And what happened then, a year later, or not a year later, a couple of months later, is that suddenly we had to stop. And then the first meeting we had after Corona started was really organized very quickly, and it was a data-minded, where they improvised a little bit, as you can see here on the pictures I have of this event. And here we are, a year later, and we seem to have adapted quite well. And one of the good things about, and one of the rare good things I should add, from the whole Corona thing is that it's now easier for us to invite people from far away, such as Iceland, and we had somebody from the UK, and today we have somebody from New York, and that's Laura Dierik, who will start in a couple of minutes, and she's from the Flatiron School in New York, and she will talk about data science education in the US. And then we'll have a group of people around Frédéric Lebeau from Data Village, and they will talk about privacy and some related subjects. And finally, we'll have Janou from the University of Antwerp, and she will tell us something about AI systems on digital footprints. I'm going to cheat a little bit and see if, okay, so the next slide is the usual suspects. So if you think you have a subject that might be interesting for people who are following us here, you can reach out to one of the folks that you see there. And then I have one final slide, and that is the next meetup, which will be on the 20th of April 2021, the 36th meetup by then. And I don't know whether we have already announced officially who will be presenting them, but what I can tell you now is that there will be a talk on R-Shiny, and there will be some PyTorch in there. So interesting stuff, I guess, for all of you. But now, without further ado, let's go over to Laura Dierik from the Flatiron School about data science education. Now, let me see here. I have to go a little bit down. All right. Okay, great. I guess we're all set. Laura, the floor is yours.
Thank you so much. I'm assuming everyone can hear me. Thumbs up. Yes, got a thumbs up from Lean. Yeah, thank you all so much for having me. It's really exciting for me to speak at this meetup because I was born and raised in Leuven, so I have a very strong connection to the city. I would say born and raised and studied in Leuven. So thank you so much for giving me this opportunity. Tim Verdonk, who asked me, and then Linde Vloeberg is actually a good friend of mine too. So I really appreciate being here. As Istvan said, I'll be talking about working in data science education in the United States. Inevitably, my work is connected to my company, so I'll be talking a little bit about what my company does. I hope it's not too salesy. I don't think this is the right audience for sales at Flatiron School, but I'll be talking a little bit about that, and then I'll open up for questions afterwards. So, as I was saying in the beginning, I was born and raised in Leuven. I studied in Leuven my bachelor and master handelsingenieur, and then I went on doing a PhD in business economics in Leuven under Gerda Klaaskes and Bart Bases. Some of you may know them. After graduating, and I graduated in 2015, I worked as a curriculum lead at DataCamp, and this was right when, and I don't think I need to introduce DataCamp for anyone here because we're all Belgian or people with a Belgian connection, I assume, but DataCamp is a data science, an education platform to learn data science. Right when I started working at DataCamp, they had got seed investment funding in Boston. So I basically moved to Boston straight after my PhD, lived there for 1.5 years. Afterwards, DataCamp moved to New York with them, and then stayed at DataCamp in total, was there for about 2 years. And then I got the opportunity to join Flatiron School. And Flatiron School is a for-profit educational company. So we basically, the core of our business is we train people to become data scientists, people that actually have zero data science experience, and train them up until they can basically start a entry-level data science job. And this is a 15-week program. And when I joined the school, we didn't have a data science program yet. So I built it out along with 2 coworkers. We started in New York only. Now we have 8 campuses in the US. And as I was saying, we only had a software engineering program when I joined. Then data science was the second one. Now we have cyber programs as well as UX UI design programs as well. So we've been growing quite a bit over the past few years. And I just want to join this trend of doing a how it started and where we are now. So this is how it started. I guess how it started. This is my PhD defense. Doing really heavy modeling, and this is a presentation I gave then. And this is how it's going. So for my company, we have actually started doing YouTube ads for our data science program, and I'm in that YouTube ad, and in this ad I actually explain in 2 minutes what deep learning is, and the application is recognizing breeds of dogs. So this is still in that YouTube ad, and the interesting thing is that every time I watch YouTube, I get my own ad, which is definitely confronting and not always fun. And Flatiron School actually pays for me watching them then. So I try to not watch up until 30 seconds because that's when they start being charged. So anyways, let's talk a little bit about the data science education landscape. So I guess how I'll structure this conversation is I'm talking about just like data science education in general, where Flatiron School is, and then how, I guess, and it's really important to kind of understand the mission, to understand the work I'm doing, and how I'm trying to do the best thing possible to keep our data science program cutting edge. So this presentation will definitely be more of a business presentation and not very deep data science by any means, but just like kind of give you an overview of what we're doing. So if you look at the data science education landscape, and obviously there are many more companies, I just highlighted a few that I know, you kind of can look at this continuum of companies that either start from more of like upskilling people in data science, so teaching them small things like, intro to R, maybe like scikit-learn, intro spreadsheets or intro to SQL. That's very much how DataCamp positioned itself. Not to say that they don't have like bigger programs. I know that they also have like combinations of courses on their platform to then build up to, basically like a more transformational experience. But I would say that both DataCamp and, for example, DataQuest they provide more modular courses and modular learning in terms of what data science or data analysis means. Then at the very other end of the spectrum, you have what we do right now. Flatiron School, for example, and Lambda School it's really like more of a transformational experience. And that's also really how these companies are positioned. So in Flatiron School, it's truly about, we're going to transform, you're going to learn a 21st century skill, and we are going to transform your life. And this is particularly true in the US, where gaining this skill is extremely valuable, and there are so many jobs in the job market right now. So that's kind of like the continuum of where I see these education providers. And then Coursera and Udacity is somewhere in the middle. They do longer courses, but not all of them are truly transformative. Whereas Flatiron School and Lambda School is like, all we do basically is really transform people's skills so they can totally become data scientists where they weren't at all before. That's also reflected in the mission to enable the pursuit of a better life through education. And #changing. We're big on social media, as you could see in the in my YouTube ads. And that mission means that there's actually a true commitment to transparency in terms of job placement and also closing the gender gap. So what does this mean? It's truly important for us. We're saying that we're, pursuit of a better life. So that's a big commitment, and that's a big promise. So what comes with a big promise is also transparency on delivering on that promise. So what we're doing as a school is every year we publish our job outcomes reports, and it contains all sorts of information on job placement, how people are doing in the job market, and also closing the gender gap, because that's one of the main priorities of the school, is really work on gender parity in tech. And I'll just go over a few pages of the job placement of our job report of 2020 to give you an idea of what that looks like before kind of going into my role and the curriculum and how we go about designing the curriculum. So, and I need to give like a side note of that this is the job placement, our job career report for 2020, which was obviously one of the most challenging years for us to place people in jobs. We have a career services team. In fact, Flatiron School's career services team is the biggest team in the company. So when our students graduate after their 15 weeks, there is like this just true army of people that just like puts everything into making sure that those alumni will get a job, because of these yearly job reports, and because we do promise job placement. In previous years, our job placement was always more than 90%. In 2020, it was 86 for all our disciplines, as you can see here in this chart, which is actually a pretty nice achievement, knowing that many data scientists lost their jobs, actually bringing up the bar of what's expected for you to know as a data scientist. Because what happens is many experienced data scientists lost their jobs, and they will go into other data jobs that are potentially have a lower bar or more entry level, just to make sure that they continue their employment. So we actually did see that was harmful for our graduates, because these are people without any experience. So to make sure that they were placed, definitely required extra effort and an extra push from us to make sure that happened. But we succeeded quite well. Closing the gender gap is the main reason why I wanted to work for Flatiron School, because being a woman in data science definitely is interesting at times, and you just notice, you look around you, and they're not. It's generally more male than female in the industry. So just kind of pursuing that and encouraging women to do data science was something that I was very passionate about. So what we're seeing is that we're graduating 33% women, which is still lower than 50%, which is the goal, but it's better than general, computer information science bachelor's degrees in the US. We also see that actually the placement rate for women is a bit higher at Flatiron School, which is really exciting. So we see women be very successful in our programs and after graduating. And then just to close off the kind of like job placement reports of this is, so we're saying pursuit of a better life through education. Of course, the salary matters here, especially in a country like the US, where there's definitely a big gap, and there's like a very widespread of salary ranges. So what we're seeing is that we have like pretty good starting salaries. We truly have people coming into the program who double their yearly salary, who before were shop clerks or bartenders or all that sorts, who were more at salaries of like 40, 50,000 a year or less, and now go into salaries of 85 up to $98,000 a year in Washington, D.C. So definitely just really exciting to see what can happen in 15 weeks. And that's, you know, one of the main reasons I'm really excited to work there. Great. So now a little bit, and all this context, because I think it's really important to understand why we're working how we're working. It's just because the focus is so much on making sure people land these jobs. So what we need to do is also be very aware of what are important skills in the job market to make sure we really teach the right program. Because how we're truly looking at this is we have 15 weeks to teach the skills that are, you know, to teach the skills that are as valuable as possible to ensure that these people at the end of their journey will actually go into the job market and be successful. So I'll talk a little bit about that curriculum improvement. And I originally joined Flatiron School purely to work on curriculum. Now I have like a hybrid of responsibilities that are curriculum and just like general thought leadership and managing a team. But curriculum is still a really important part of all this. So how do we think about our curriculum? So this is essentially our data science program the way it looks right now. So just so everyone knows here, we're very Python focused. We don't teach R at all, simply because we have 15 weeks to teach the most important things. And we believe it's more important to master one language really well and not just like have like know a ton of languages and then not know anything in depth. So we want them to know Python very well. And we're teaching SQL as well in the first phase. Phase 2 is really the stats phase, where we teach distributions, probability theory, testing, and then we end that with linear regression. Phase 3 is truly the machine learning phase, where we teach scikit-learn front to end, also understand all the algorithms behind the machine learning methods. And then phase 4 is our advanced methods phase. And then in phase 5, we have the data science project. And just to be clear, our program is in general very project-based. So when I say our phase 1 and phase 4 are 3 weeks, it's actually each of these phases is 2 weeks, and then the last week is a project. So that means that in total, our students have 5 projects that they will work on, upload in the GitHub repo, and basically package all together. And these 5 projects are truly their portfolio when they exit the company, exit the program, and then go into the job market. So this, as I said, this is the data science program. And then when we built this about 3 years ago, it's like the focus is really on data science. But then, you know, we have all these students that graduate, and we realized that, you know, we have so many titles when people graduate. So what this is a word cloud of all the job titles that our alumni initially land in their first job. And this is, I pulled this data a while ago. This was back when we had 400 alumni that had landed jobs. And out of those 400 people, there were 216 unique titles. So it is kind of, this means a few things, you know. First of all, I think the data, many companies are also kind of not sure exactly what data science means or what data roles mean. Another thing this means is that, you know, there's just a wide variety of roles, and our students also land in very different types of roles. They're not all data scientists. Some are data analysts, some are data engineers, and we definitely see that data engineering in the job market is becoming more important, and there's more demand. So when seeing this, we're like, okay, how can we actually better cater to all these people that graduate and to all these vast type of roles? So what we started doing is we started, based on all this information, we started embarking in a backward design process of our curriculum. Already our curriculum, but we're recreating it and just like checking like, okay, how do we need to approach this going forward? And how that works is, what we basically did is we looked at the 3 main roles that we saw. So we're no longer uniquely focusing on data science. We're also looking at data engineers and data analysts. And we're going to look at what job skills and what knowledge and which abilities that people who land these roles need. And that's kind of like the end of everything. So that's where we want students to get at the end of the program. So that basically translates in program objectives. And then from program objectives, we build back to module or phase objectives. We basically changed our terminology, but we used to call our phases module. So this is module or phase objectives. And then going back to lesson and applied learning objectives. So really going from where do we want to go, and then how do we break this up in smaller pieces and elements of the curriculum to get there. And what we did to get there is just collecting, like any data scientist would do, just collecting a ton of data on what kind of information we need to know and understand what knowledge, skills, and abilities that these people need at the end of the program, assuming that they'll land jobs in the data space more broadly defined than just data science alone. So we talk to our alumni, we talk to existing employers. So we have an employer partnerships team that actually works with people that have employed data scientists. And then we also talk to our teachers to see, what they're hearing in terms of how our students are doing, what we have as feedback, etc. And then the one I want to dive in a little bit more is the current job market. So that's really important. And the good thing about alumni, employers, and teachers is that, we get kind of like all the stakeholders to weigh in. But, it's also more qualitative data. It's unstructured data. It's not people sometimes have like skewed opinions about certain things. So while they're really important, it's also important to really look at the job market data. And the way we did that is we used Burning Glass. And I don't know if anyone has heard of Burning Glass, but Burning Glass is a company. And basically what they do is they have a huge job database with all job descriptions that ever ended up online being posted in the past 10, 15 years. And so what Burning Glass does is just, they're basically scraping all the job descriptions, they're doing a ton of NLP on them, and then they basically do a summary of these job reports, and that gives you something called an occupation profile. And as soon as I got access to Burning Glass, I was just like so excited because I think it's an amazing platform. So for example, this is a screenshot I took for the data scientist occupation analysis. So you can see how many job postings there were. And just a side note, this is US only, but you can see how many job postings there were for data scientists. So about 42,000. Average time to fill is 45 days. The projected growth, then, kind of like the salary distribution, years of experience required for these job posting, education level. And then most importantly for us, is the top skills required for these jobs. And that's really what we started looking at, is just understanding the type of job skills that you need. And what we did is we looked at the top skills for data scientists, for data analysts, and data engineers, and basically put them side by side to understand which are the most important skills that we want to teach in our program going forward. So this is a quick spreadsheet that I made when using the Burning Glass data. So these percentages represent Burning Glass information on how often a certain skill, and the skill is listed in the left column, is written on a job description. So unsurprisingly, data science is written, I'm surprised it's not 100%, but data science is on the data scientist job profile 98.4% of the time. Then Python, almost 80%. For data analysts, Python is much less important. It's only listed on 21% of the job descriptions. For data engineers, it's like a little bit more than half, which makes sense. So looking at this, what we're trying to do is look at the common denominator between these and really make educated decisions on how important each of these tools is. And we really made some decisions about what we should add more into the curriculum and which topics we should potentially remove or de-emphasize. So this was a super helpful tool for us to understand kind of where we want to go as a company and in terms of curriculum. So this ended up being the program objectives in the end. So we have 8 program objectives that we are currently working on fully implementing in the program. Most of them are already there, but having these program objectives really leads us to really being more thoughtful about some of the topics that we teach. We do a little bit more data engineering now, and we're actually adding in some more topics on communication, spreadsheets, I know spreadsheets is a little bit of a loaded word in data science, but for data analysts, it's actually quite important skill to have. So we added a little bit of that into the curriculum. So this is a result of that whole exercise. So as I said, we added more business intelligence. We're going to be teaching Looker and Tableau in our curriculum, which will launch in a few months from now. And we'll be adding spreadsheets, and then we're going to emphasize SQL and more business scenarios, and also machine learning in production, something that we really haven't put a ton of emphasis on, but given the data engineering roles that are becoming more important and more prevalent, we are definitely focusing that on more. And then we will be de-emphasizing deep learning, which is, definitely an interesting point, because for us, deep learning is a really important marketing tool, because many of our students join because they really want to know about deep learning. But in terms of moving the needle when you land your first job, it just is not that important to, it's really not that important of a skill to land a first job in the data space. So we'll still be teaching it, but a little bit less. And I think that's enough. About 21 minutes in. So I know that was a lot of information. I'm really open to answering any questions you may have. And if you have any other questions about data science education, or moving to the US in general, you can add me on LinkedIn or reach me at my work email as well. So thank you so much.
Thank you, Laura. I'm sure people have enjoyed your presentation. Unfortunately, they cannot applaud as they usually do, but I will do it on behalf of them. There are a couple of questions, but before we come to that, I'm still
Ihsan, I can't hear you. I don't know. I think you're muted.
I'm sorry. So basically, we're going to go to questions, and I see there's a question from Peter who asks, and I think you touched upon it in one of your tables, but could you elaborate a little bit more on how high R skills are valued in the market versus Python?
Yeah, we can. Great. We can actually go back to this table to answer that. So what I'm seeing in the US, and to be clear, I did a PhD in Leuven, so I did only R for years. And also when I worked at Data Camp, I was teaching only R for a long time, and then I switched to Flatiron school, and there it was all Python. I was like, oh, I need to switch. What I'm seeing in the US is that because of, anything that's being done in production is easier in Python, and Python has just this wider range of what it can achieve. Python is usually the preferred language in any type of company. What we do often see is, and I've looked at a ton of job descriptions in my time now and in the past, is you often see Python and R as being like interchangeable languages that you can know. So you can also apply for a job if you only know R and not Python. But my understanding is that most likely you will have to learn, that means you'll have to learn Python on the job. So I see Python as really, and you see it in the numbers here too, for data scientists versus Python versus R. It's just, Python 3 to 4 times as prevalent on these job descriptions compared to R.
Okay, great. I see that Hans Polders is congratulating you for a great presentation. But
Thank
Lynn
you.
has a question, and the question is burning glass data? Let me show it to you. Is this burning glass data set free?
It unfortunately is not. It's actually quite expensive, and what I did is we had access to it through Flatiron School for a few months, and then when I heard we were going to lose access, I was like, I need to download, and I was allowed to. While I had it, I downloaded everything I could, and it has download capability, so I wasn't doing anything wrong. But it's unfortunately quite expensive to get to, also because it's so useful. So I'm actually sure a lot of companies use this both in their hiring and a lot of not just educational companies, but just like to understand the job market in general. So, I recommend checking it out. I have never paid for it myself. It was through Flatiron School, but it's really interesting. So I would recommend checking their website and see if there's any maybe trials available.
Great. And then one final question before we go to the next speaker, and that's a question from Dimitri, who asks, how did you end up in the US?
Good question. I guess it's a double thing, right? So on the one hand, it was DataCamp moving to the US, and I knew I wanted to work for them. But the real way I ended up here is through my first year at DataCamp. I did that through a grant of Prince Albert Fund. I don't know if anyone has heard about it, but it's basically a grant for young professionals under 30 who want to work for a Belgian company for 1 year. So how the grant works is they pay your salary for 1 year and the company pays your housing for 1 year. So that was how I ended up here in the first place. And then after that 1 year, I basically was able to extend my contract with DataCamp, worked for them. And then I was lucky to have built up enough skill to be hired by a fully American company, which is not easy remotely. But that's basically how I ended up here, and now work for a fully American company. I'm the only Belgian at my company. I think I'm the only, no, there are a few more European people at the company, but that's how I ended up here. If you have any questions, feel free to reach out to me. I could definitely send you more information about it if anyone is interested in that. So always happy to connect.
Okay, great. Thank you again, Laura. And now let's move to, that was a little bit quick. I'm sorry about that. Let's move to our next speakers. And actually, it's a whole team of speakers. And I'm not really sure where they are from. I think from Brussels or Liège or Montenegro even. I'm not really sure. They're very secretive about it. And I guess it has to do with the subject that they're working on, because they're working in the area of privacy. But I'm sure that they will tell you all about it. Okay, I'm sorry. I think we're all set. Can you start?
Yes, do you hear me?
Yes, I can hear you loud and clear. Go ahead.
Okay, thank you very much. And for the information, we have an office in Leuven, so we are.
Okay, well, there you go.
Okay, thank you, and good evening, everyone. Thank you for the opportunity to talk about what we do with Data Village. And we will talk about unlocking the value of personal data with user control, privacy, and transparency. So very briefly, Data Village is a B2C2B personal AI startup with a focus on data value extraction with respect of consumers' privacy and control. And our vision is a fair personal data economy benefiting for both the organizations and their consumers. So the speakers today from Data Village, Philippe, the tech lead, full stack semantic, Loic, lead data scientist, and myself focusing on product and architecture. So most of us today use, as you know, digital devices more or less every day, which means that every day we create a stream of online activities, and these are our data. This is an ever-growing database of personal information that determines our online behavior. And the model of today is wrong. At least this is what we believe. And the data is locked, the market is closed, pushing the organizations to collect more and more data, and personal data is spread and duplicated, making it impossible for people to keep control over it. Based on market surveys, 91% of people feel like they've lost their privacy and control, and 36% feel they have no choice about how apps use their data. We have been working on this topic over more or less the past 2 years, and nowadays there is no single day without something related to personal data control and privacy, like the announcement from government and regulation, the issue with the way GAFA grab our data, or multiple scandals about the use of our personal data. But the good news is that a paradigm shift is underway, and a paradigm shift that puts users at the center of the equation and gives them back control over their personal data, pushing the organizations not in the race to collect more and more personal data, but to focus on their product and services. And in this new world, there is one new technology and a solution. There are multiple new technologies and solutions. And one of these is about Solid, a standard protocol to create and manage personal data. Philippe will talk a bit about that.
Yes, hello. Thank you, Frederic. So as Frederic explained, there is a paradigm shift that's coming. And I will talk to you a bit about Solid, which is one of the major disruptive actors that will probably help in that shift. So Solid is a project that's been initiated by Tim Berners-Lee a few years ago at the MIT. It now has a large team working on it, including some very talented people at IMEC Ghent. So the objectives of Solid is to bring back true ownership and control of data to the individuals, to the users. So it means no more vendor lock-in of the data. And it's also about achieving some of the original goals of the web, as Tim Berners-Lee devised it. That means a truly decentralized data graph with read-write capability on every end. So the current status, what is it? So we have, as we know, we have a few major actors who hold our personal data in closed data stores, in silos. So our personal data is scattered across many silos behind proprietary APIs with very limited access. We cannot go and get our data as we would like to. And we usually have specific identities for each of these providers, even though sometimes you have the same identity that you can take from one to the other. We have several identities. In terms of the ecosystem of applications, of third-party applications that can be built on top of this data, well, there are not that many third-party applications, mostly because, as I said, these data are hidden behind walls, sometimes paywalls. So it's quite hard for a new kid on the block to come and define and implement a new service as a third-party application. So where does Solid come into the picture? Well, it will help deconstruct these silos. Solid means that every individual will have a personal data store that is controlled by the user himself, using open standards, using a unique web ID that you can use across applications. And so you will have a true linked data graph of your digital twin that you have control on. From the perspective of the third-party applications, since there is no more vendor lock-in and data silos, there will be a lower cost for new applications to come in and implement services on top of user data. So all those actors, be it the major actors that we know today or new applications, will be on the same level. So how does it work? What does Solid do exactly? So instead of the data stores as silos as we know them, every person, every individual can register with some Solid provider of its choice to have what we call a pod. So that's a personal data store to contain, to hold all his information. Technically, the whole technical stack relies on representational state transfer, REST, HTTP, RDF, with a special focus on decentralized web identities, decentralized linked data storage, and open standards for interoperability. So I will talk a bit more about interoperability because that's really crucial here. So having a pod, what does it mean? It means you have to register with a pod provider. That means anyone who wishes to implement and expose a Solid server as per the spec. That can be a private company. There are some already. That can be a government. For instance, the Flemish government has announced that it will provide pods to its citizens. Or it can be some device like a Raspberry Pi in your basement, your choice. So at that point, you may say, yeah, okay, well, a Google Drive can be is sort of that. Well, yeah, but Google Drive is not really interoperable. It's not open. Just try to easily move your data from a Google Drive to, for instance, another provider. That won't be easy. So interoperability is really what guarantees that you won't be bound to a specific pod provider. That means that your personal data in your pod can be easily accessed by any third-party application, regardless of the implementation. And very importantly too, you can, as a user, you can very easily migrate from one pod provider to another without an effort and while keeping your web identity. So if we focus a bit more about on what the interoperability means in this context, there are mainly three levels where interoperability is at stake in this solid stack. Authentication, I talked a bit about it already. So in the solid solution, you get a web ID, which is a standard. That means that you get basically a URL that identifies you, and it's decoupled from the pod provider. You keep it with you, even if you change a pod provider. The interoperability of the APIs, how you access the data. So as I said already, the Solid strongly relies on standards like HTTP really as the applicative protocol. So really use a really RESTful approach. And then most importantly, you need to know what you're talking about when you fetch data. So Solid is based on RDS, so it's basically a triple store. But you need to use shared ontologies to exchange data with other people and agree on the semantics of the data. So you have to use ontologies like you have schema.org for as a common ontology. Solid is also defining a shape repo that contains what they call data shapes. So all of that, all this Solid solution is a mean to bring a new open ecosystem that will help get much better application where the data is really under the control of every individual user. There is no longer a prerogative for the actual major data providers to control or host your data. You can move from one provider to another. And most importantly, there is no longer an unfair advantage for these major actors who have locked in your data. Any new application is entitled to have access to the data, and so it is an ecosystem with a much more healthy competition. Thank you, Frédéric.
Thank you, Philippe. And next to this concern and solution about Solid, meaning mainly data control, data sharing, and privacy, there is clearly another thing that is growing, and it is about interest of personal data by organizations, especially when it comes to hyper-personalization, augmented experience, insight extraction, and so forth. Just have a look at the economic model of big players like Google and Facebook. This model is also called behavioral surplus. The strategy and their strategy is clear. They get personal data to generate personalized product and trigger addiction. Then they obtain more and more data to generate surplus like your consumer profile and sell it in a very lucrative advertising market. And this is a closed market without transparency and a very, very limited user control. So more than data sharing, we think that the real opportunity for this paradigm shift lies in combining data from multiple sources to compete and to create new personalized products with respect for consumers. So imagine that you could get a view and control all of your data. Imagine that as an organization, you give back these data to your consumer, to your user, but you can also use data directly from your users. And you can just pick and choose the data you need, extract insights or behaviors without the burden of managing that data, especially in regards to regulations. And all of this with full privacy, transparency, and in respect of your consumers. So how does that work? A brief and very high-level explanation about the mechanics. So in the first stage, the user, as explained by Philippe, links or creates his personal data store, for instance, a Solid pod. Then the data providers writes data into personal data store according to a user-centric data model. And obviously, today, these personal data stores are empty. So as from day one, there's no data in this store. And we give this opportunity to connect existing data source with your personal data store. Then service provider integrates what we call a data passport into the existing user experience to get consent and access this personal data. And then these service providers who use what we call a data cage, it's a personal AI environment, which is based on confidential computing. And there they can perform AI data enrichment and matchmaking between their product and any kind of personal data. Then the service provider use these outputs, and only the outputs, so not your raw data. So they use this derived data into user experience to create new personalized service and product. A very nice example, basic example that we are working on, by the way, is in the media industry. So user navigates with their data from one platform to another, and they use this data to get recommendation and discover content across multiple platforms. And Loic will give you more explanation about what's happening within this data cage.
Yep. Hi, everybody. So I will give you just a high-level example of what we can do for the media industry by using the data in the pod, in the personal pod. So let's start by the data sources that we may have. So first we have the media metadata that we can recommend. We also have user-centric data, so typically previous actions of the user on various platforms, Facebook, Spotify, maybe Ovio, or other kind of platform. We will connect all that together. And then what we will do, we will enrich the data in this data cage in two ways. First, we will do what we call graph enrichment, and we will also do NLP enrichment. So first, graph enrichment, we will try to connect action of the users through the media we can recommend by playing connections between these media and possibly external concepts. So typically we know Mick Jagger is one of the members of the Rolling Stones. That is a group of rock music. All that will make connections between these various concepts, and those might be connected to some media. So what we will do, we will try to find connections between media by taking the shortest path in this data graph between the two media. That's a similarity measure. We will build two other similarity measures in this example based on natural language processing. So one that is very simple is just based on the number of words shared between different media. So that's very basic TF-IDF algorithm. It's not in general very powerful, but we can refine a bit by using not words but shared named entity between the media, and also build a similarity measure between pairs of media using these either shared words or shared named entities. If you move, yeah. Then we have at this point 3 different measures of similarity between medias. We will combine them using weighted sum or weighting function to compute an overall similarity between all pairs of media in our data cage, and we will try to connect those to the action made by the user. Frederic, if you move.
Please.
So there you can see the full view from A to Z. So we start from the user, that is the red dot here. We have the user action that are registered in the data pod of the user. We see what type of media the user touched, what he liked, what he followed, what he bookmarked on different platforms. And we know also those media, how they are connected to similar medias using the similarity measures we built on the previous slide. So from there, we can recommend media centric to our user. And what is nice with this approach is that we can navigate the graph also backward to go from a recommendation and explain to the user why we made this recommendation. So we can navigate the graph backward and say, okay, we are recommending you to watch this new media because you liked that other media 2 days ago. And this is what we are building now.
Thank you, Loic. And that's it. So thank you all for your attention. There is a clear set of challenges and benefits in such a user-centric approach, combining technologies like Solid with consent-driven governance and confidential computing. And one of the key elements, I hope that you have seen that within the presentation, is about interoperability and the user-centric data model, which is really the key element that gives the opportunity to bridge data together from multiple sources and use this data in this specific use case to provide recommendation across multiple platforms. Thank you.
Okay, thank you very much, Frédéric, Loïc, and Philippe. There are quite a lot of questions, so let's go over them. But I would like to start with not with a question, but with a remark from the fabulous Hildegard van Oven. And she says, if you want to implement this in reality, I think it would be wise to try to convince the European Commission. They are very aware of privacy issues and sensible to it. That's, I guess, food for thought. But there is a related question, I guess. And let me see if I can find it back. Yeah. So the question, I don't know whether it's related or not, but I'll give you the question as it is. And it's coming from Bruno van de Castelen. And he asks, how realistic is it to try and roll this out? Can we aim for snowball effect when more and more companies join? Or would some legal forcing be necessary?
It's a very good question. And I don't think this is there is one or another. It's a bit a mix of both. So the snowball effect as a startup, this is what we hope. So yes, so we hope that once there is one actor joining, one big actor joining the movement, the other one will follow. Nevertheless, this is also to trigger this. This is why we bring already existing actor on the market and bringing the data already into the system. So that's how we manage what we call the cold start. And yeah, obviously for legal forcing, we rely obviously on GDPR to enforce in a way the fact that user will get back their data and their raw data, especially into their hands. That's how we see the rollout.
And Frédéric,
yeah, please, Philippe.
Yeah, if I may add, so you mentioned the GDPR very rightfully. That's a major, a major argument and then there can be also very important initiatives like the one I mentioned for instance, the Flemish government, who announced that they will offer pods to their citizens that will help adoption. And it's certain that we should not expect major players like Facebook and Google to be early adopters of such a solution. But once we reach a critical mass with that kind of initiative, we can maybe hope for that.
Okay, great. Thank you. The next question is from Peter Coussement, who is in good form today because he already asked quite a few questions and remarks. But his question is, I'm not going to read it out loud. You can see it on the bottom of the screen, but basically he's asking about how can we make sure that the bigger players are involved?
So it depends, what do we mean by big players? If we talk about big players like the GAFAs and so on. So yeah, as Philippe said, there's no a lot of incentive for them, at least now, to go in that way. The way they are moving is to acquire more and more data, and nowadays is by acquiring more and more companies to get the data from these companies. So for big players, this is not clearly not a lot of incentive. Once we talk about big local player, there we see opportunities for them, especially to compete with big player and global players. If you look about media and streaming platform, combining, multiple streaming platforms through the consumer could make sense to compete with players and major players like Netflix.
Okay, great. Thank you for that answer. And now we have a question from our very own Chris Peters, who asks, assuming you have consent from a whole bunch of customers, any algorithm you run on the data will be incredibly slow, given its spread over all these spots. Am I right? That's his question. So how can you mitigate that?
So I would say that once we have 1 million customers, we will have time to think about that. So that's not exactly the thing we are thinking about right now, but it's a good question. We already see it right now with a set of users. We have to look about performance, that's for sure. Nevertheless, so there is also why we bring this data cage into the picture. We'll not have time to explain too much about that, I think, today, but directly loading, and getting data from the pod for processing each time could take a lot of time. So that's why we see this component in the picture, especially to mitigate, the time for processing. But then it means that this component has to ensure also full control and privacy.
Okay, great. Thank you again. And there is Peter, who also has a question, I believe, related to these pods. So he has missed a bit on the connection between the pods and the data cage. Can you elaborate on that?
I don't know, Loic, if you want to reply, or do I?
Go ahead.
So the link is, so as I just said, the pod, we consider the pod as a personal data lake, meaning you get your raw data and you keep your raw data in your personal data store. Then there is a cage, and a cage is not one cage per user, it's one cage per client, meaning you have one cage per client, and the clients can then load this raw data into the cage, but they can also load their product data. And this is there that you have the enrichment and the processing, meaning the enrichment on your product data and on the personal data that have been loaded into the cage. And we ensure that only the derived data can come out of the cage. So that's the difference between the pod and the cage. It's about processing and storage.
Okay, great. Thank you very much for this nice presentation and for all the answers that you gave. Thank you, all three of you. And now let's go over to Janou Ramon from the University of Antwerp. Add her to the stream. And she will present something about AI systems and digital footprints. And I hope, of course, that there is no clash with the previous subject, but I'm sure that Janou will tell us more about that. Janou, the floor is yours. I think you are still on mute. Can you unmute yourself?
Yes, I think I'm unmuted now. Okay.
You are now. We can hear you loud and clear. Thank you. Go ahead.
Okay, great. So hi all, and thanks Sven for the introduction. And I'm also very glad to have the opportunity to talk to you about my research tonight on gaining insight into AI systems on digital footprints. So I'm Janou, and I'm currently working as a researcher at the Applied Data Mining Research Group here in Antwerp, with Professor David Martens as my supervisor. And at this research group, we have a main focus on building machine learning applications on big behavior and text data. So mostly we focus on classification tasks in a variety of domains, ranging from fraud detection to marketing to credit scoring and so on. And on one hand, we focus on the more traditional data mining steps, from finding the best pre-processing techniques to finding the best modeling techniques and so on. On the other hand, we focus on, we go actually beyond the predictive modeling, and we focus on explainable AI or interpretable machine learning, so both buzzwords at this moment. And this means that after training and tuning and testing the prediction model, we also go move on and actually go on with interpreting and probing these models to try to understand how these models make their decisions. And we do this on the model level, so yeah, over all the possible decisions that a model can make, but also on the individual level, for example, to try to understand how the model comes to a single prediction. For example, based on which websites that you visited, does a model predict that you might be interested in this data science meetup, for example. So this is really, in a nutshell, what we focus on here in Antwerp in our research group. Now here's an overview of what I'll be talking about tonight. So first I'll explain why interpretability issues arise from prediction models on these very big behavioral data. Then second, I'll immediately come to the contribution to actually what I've been working on in my research. So we proposed rule extraction with meta features as a solution to gain insights into these models on behavioral data. Then next, I'll go on and discuss some main results from our paper that actually show the effectiveness of what we proposed as a solution, so the rule extraction. Then later on in this talk, I'll describe a bit more why actually we should care about interpretability. What does it mean for researchers, for businesses to actually peek into these black box models and understand how they work. And then finally, I'll wrap up this presentation and meet up with one summary slides. So in my research, I actually focus on these big behavioral data. So machine learning applications on these data. And today, I think you can, you agree for yourself that we actually all have a digital twin, as a lot of our behavior is captured online by using our mobile phones, by wearing wearables, by interacting on the internet, and so on. For example, the music that you listen to is captured by Spotify. The locations you visit are captured by your mobile GPS. The searches you make on Google are captured. Online payments you make are captured, and so on. And all of these behavioral data is actually very predictive for many interesting applications, business applications. So we can start mining this data to predict variables of interest. For example, the payments that you make or the social media data that you generate can be predictive for your creditworthiness or for in HR applications for your suitability for a job, position, for example. Another example is the web browsing data, so the websites you visit every day or the searches you make on Google. They can be very predictive for whether you're interested in a product or not. So, and this then can in turn be used for targeted advertising, for example, just to give you some of the many examples out there. Now, to illustrate the type of data that we're focusing on here, this behavioral data, consider this Facebook data set, which is actually coming from the research from my colleague, Sine Praat, and she used this Facebook-like data to predict people's political interests. So whether they have a center or a right or left political interests. So, and first of all, as you can see, every Facebook page results in a separate column, a binary column, which then actually results in a very high-dimensional data matrix. As a second very typical characteristic is that this data is very sparse. So it's horizontally sparse, as one user only will like a small fraction of all possible pages out there. So, and that's very typical for these behavioral data in general, as people actually have a limited behavioral capital. You can only visit a limited amount of places in a day. You can only make up to a certain amount of payments each day, and so on. So it's horizontally sparse, but it's also vertically sparse, meaning that every page is only liked, again, by a small fraction of all people in the data set. So this then results in a very sparse matrix that is reflected by a lot of zeros in the data matrix. And here, you can see this, that every it's not represented by zeros and ones in this data matrix, but here every like icon will then actually have a non-zero value in the data matrix. Now, using this Facebook data, we can then start training a predictive model. And here it's in our running example, we want to predict whether someone is a right, a left, or a center political voter. Now we can use this labeled data, so the Facebook like data, with the target variable. Here it's the Y array. We can use this labeled data to do the typical data mining things, so to train, to tune, and to test the model. So here it's very simplified. But then once we did all these data mining stuff, we end up with a good classifier, which we can then use to start making predictions. So here it's the predictions on the political interest, represented by the orange array Y hat. Now, often these predictive models on behavior data are very accurate, and also in this paper of Sina, she actually comes to models that are very accurately predicting political interest from what people like on Facebook. But at the same time, these prediction models are also very complex and opaque in nature. So they have these interpretability issues. And for nonlinear models, like, for example, random forest model, it's impossible to immediately interpret how the model is making its decisions. But even for linear or rule-based models, it's no longer straightforward using this data, because of this data, to interpret how the model works. And it stems again from these data characteristics, dimensionality. So every Facebook page in this example has a corresponding coefficient, for example, in the linear model. So it's very high dimensional. But also, you might now think, okay, why not just investigate the top Facebook pages with the highest corresponding coefficients? But then it's also not very helpful because of this sparsity. So a Facebook page is only relevant for a small subset of all people in the data set. So this results in interpretability issues that we want to, that's actually our main challenge here that we want to solve. And in the literature, there's one group of methods that's called rule extraction. That's the method that actually is sort of surrogate modeling method. That's where the goal is to try to mimic the predictions of this more complex model. So here it's the model on all of these behavioral features, to mimic the predictions of this model with a small set of explanation rules. So, and why a small set? Because we want to limit the complexity of this set of rules, of this explanation, because we don't want to just replace the model again with a set of hundreds of rules, because then again we have this interpretability issues. And then also an important thing here is that we no longer want to use the ground truth labels to extract these explanation rules, so the true political interest in our example, but we want to use the predicted labels, the predicted political interest, to actually obtain these rules. Now, actually for doing this rule extraction, the same challenges hold. So the same challenges that actually come from these characteristics of these data, so the high dimensionality and the sparsity, and the fact that often there are very many relevant predictors for the prediction task at hand. So these challenges did not magically disappear here. So that's actually our main concern again for doing rule extraction. So we are concerned it will fail because there's this trade-off between having many rules or needing many rules to explain a large fraction of the model's behavior, or having a very parsimonious explanation, so a very small set of explanation rules, but actually ending up with an explanation that's not very reflective of the model's behavior. And so that's the challenge that actually has inspired us to, or started us, left us thinking about how to solve this. And we came up with the following. We thought of using another representation of the data to actually do this rule extraction. So we no longer want to do the rule extraction with the original features on which the model is built, but we want to go to a higher level representation, which we call meta features. So what are meta features? For example, for the Facebook likes, we can group similar Facebook likes into categories. For example, Facebook pages, actually. Facebook pages about data science or machine learning can be grouped together, or Facebook pages related to fashion, for example. So we can have these different categories, but also for other types of behavior data, you can do the same. For example, for locations, you can group coffee shops together, you can group sporting venues together, and so on. So for all of these behavioral data, we can do something like this, and that's the intuition behind having these meta features. Now, more formally, what we actually do is we go from the original user Facebook page representation, so the actual original data. We go from the original data to user meta feature representation, which is here shown on the right. And we go from one to another using a mapping matrix. So that's the one in the middle, where you actually see that every Facebook page belongs to a certain meta feature. And so actually the resulting meta feature representation has fewer dimensions, but also it's much less sparse than the original representation. And that's very important. So, for example, you can imagine that liking the magazine Cosmopolitan, for example, is not very relevant for a lot of people in the data, but much more people will probably have liked a Facebook page that's related to female or fashion magazines, for example. So the coverage of the meta features is much higher compared to the original. And in this mapping matrix in the middle, it's either fixed. So for example, for Facebook data, you already have these categories that are available immediately from the data, but you can also obtain it via data-driven methods. And in our research, we use a non-negative matrix factorization to obtain this mapping matrix, but you have a lot of different alternatives to experiment with, of course. So this is what rule extraction with meta features looks like visually. So here on the left part of the slide, you again see the data mining, steps. So the classification step. So building the classification model. But then on the right part, you see the explanation part, where we actually want to explain the prediction model using no longer the original data, but the user meta features representation. So that's important. And we also don't use the true labels, but we use the predicted labels of our model, because that's what we want. We want to gain insight into how our model behaves. And then we can, using this meta features representation and the predicted labels, we can extract rules. And in the paper, we use a card decision tree algorithm. Now let's look at an example in our Facebook running example. And here, so this is an example of explanation rules to explain a logit model on all Facebook pages. Now here, it's not yet what we propose. Here, actually, we extract the rules with the original data, so with the Facebook pages themselves. So, and here, for example, the explanation shows 4 rules on how the model is classifying people as a right-wing political voter. For example, when they liked the page Bart de Wever and the news page HLN, the model predicts the person as a right-wing voter. Now, what we propose is this. We propose doing this rule extraction with meta features, and that would look like this, for example, in our Facebook prediction model. So here you have 3 explanation rules that actually show how the model is making its predictions, but now with the meta features. So for example, when someone liked more than 26% of the pages related to right political parties, fewer than 8% related to left political parties, and fewer than 6% related to the environment, then he or she is predicted as a right-wing voter. So here I show you the meaning actually of these meta features in terms of a word cloud that I built. So here it's the top weighted pages that belong to this meta feature, obtained via NMF procedure, just to give you some intuition on what's actually inside these meta features. And what I find interesting, maybe to tell you here, is that this meta feature explanation actually also gives different types of information on how the model behaves. So here it shows that there's actually a trade-off between the amount of pages that someone can like related to the left political parties or related to the environment to be predicted as a right-wing voter or not. So here, the more pages someone likes related to left political parties, the fewer pages he or she can actually like related to environment to still be predicted by the model as a right-wing voter. So actually a nice insight that immediately can be seen from looking at this explanation. Now that brings me to the main question that we wanted to get an answer to in our paper. And that's the following. Do these explanation rules extracted with meta features actually result in better approximations of the model compared to explanation rules with the original features that the model uses, so the original fine-grained behavioral features? Now, how do we formally measure this? For this, we use a metric that's called fidelity. And fidelity is actually the fraction of the predictions for which the explanation rules agree with the prediction model. So it's no longer, so here it's actually, you can think of this as having a third column where you have the predictions of the explanation rules. And now you want these predictions to have a large overlap with the second column here, the predictions of the model. So fidelity is actually the accuracy of your explanation rules with regard to the model predictions. So it's not accuracy what we normally would have as the overlap between the first and the second column here. So that's just the accuracy of your prediction model. But now we want to have a high fidelity, so a high overlap between the predictions of the model and the predictions of the rules. Now here are some main results from our paper, where we actually built these explanations, so explanations for a logit model, but also for a random forest model, using a benchmark of 9 different data sets. So here these data sets are shown on the x-axis, and on the y-axis you see the difference, the percentage difference in fidelity of explanations with meta features versus explanations with the original features. And here we found empirical evidence for our hypothesis. So indeed, meta features give a benefit in terms of better approximating the underlying model. So these positive values that you see here on the graph actually show that using meta features for the explanations results in better approximation, so a higher fidelity compared to explanations with the original features. And generally, we have these larger improvements. So the more you go to the left on the figure, so data sets where there actually are larger improvements, larger benefits from using meta features. That's because for these data, the sparsity issue, or actually we have strong indication that that's the case, that the sparsity issue of the top predictors in the model, so the top behavioral features that are the most predictive in the model, that they are very sparse. So that's also, again, what we would have expected, and that's also that was our starting point in the first place to do this kind of research. But there's more about more to it, but I'll leave that to you for reading my paper afterwards. So I explained to you why there are a lot of interpretability issues, coming from models built on these types of data. And then I showed to you what our solution is, what we propose, rule extraction with meta features to gain insight into the model's behavior. And then our results show the effectiveness of our solution and that it actually works. But now you might wonder, okay, why care in the first place about interpretability? What does it mean? Why not just deploy the model in the wild? And generally, there are a lot of motivations why it can be very interesting to have model interpretability. And I grouped them into 3 categories. So the first is to validate your model and to gain insight into it. So to give a concrete example here, think about targeted advertising based on the websites you visit. So first of all, as a company, you're very concerned of having a model that's actually accurately targeting people that are most likely to be interested in your product or subscribe for your service. But then second, it's also an interesting question, a business question, like who are we actually targeting here? It's interesting to have better insight into the preferences, the profiles of these people you target. What are the most predictive websites or groups of websites that actually explain why the model is targeting those people. So this can also further guide the strategy of your company, your marketing strategy, and so on. Now, next to this validation and insight reasons, there's also ethical reasons to it. So AI systems are more and more used in critical domains like HR or pricing or credit scoring, recommender system, and so on. And there's a large concern that these models or these algorithms might pick up some unwanted information, for example, on protected variables like gender or sexual orientation and so on, which they cannot base their decisions on. And one very notable example is about the Amazon recruiting tool a few years ago. So what Amazon did is they built a recruiting tool and actually a screening tool to automatically screen resumes to see if a job applicant is suitable for a certain position or not. And it turns out that this recruiting tool was very discriminating against female applicants. So it was actually downgrading applicants that had resumes with words like women's chess club captain. Also, people coming from female colleges were also downgraded by this tool. And in the end, they had to scrap the tool because, of course, it was unacceptable. So this is one of the many ethical reasons you can think of, but there's also a lot of concerns nowadays also discussed in the media how algorithms could actually drive this online discrimination or indirectly discriminate because they or discriminate by association and so on. So these are very timely issues which can be summarized as these ethical reasons to have interpretability and to not just blindly trust your model to be used, to be deployed. Now, third, There's next to these ethical reasons, you also have data science reasons to not just not know what your model is doing, and to actually be able to monitor your model, but also to find issues in your data set and so on. And here I have an example, text mining example, using a publicly available data set from, so it's a 20 news group data set, where we do topic modeling. So here in this example, we want to build a classifier that's actually able to distinguish between news articles about atheism versus those who aren't. Now here again, coming back to the topic of this talk, here we generated explanation rules with the actual words in it. So just original data that the model is working on. So the original model is a logit model on all the words, and here you see explanation rules with the words. So at first sight, it seems reasonable. There are words like atheism or choose or exists or morality in this explanation, so it seems reasonable, and also there's no immediate red flags in it. But if we then look at the explanation rules with meta features, so the clusters of words, we see different insights coming up. So here's at the top node, there's this meta feature that actually groups or summarizes posts that are written by a certain particular person in the data set who's called Bob. And it actually summarizes his signature quote that he always uses at the end of his news articles that he wrote, always about atheism, of course. And actually what the model did, it started memorizing his signature quote, also his name. And of course, this type of information would not generalize well to new data. So this is a very interesting insight, different type of insight that comes out of this explanation when you compare it to an explanation that was just based on the words that the model was trained on. Now, I'd like to conclude with some final key takeaway from this talk, what I like you to remember from this talk. So to gain insight into prediction models on big behavioral data, you can use these higher level, less sparse meta features to explain the model, to do rule extraction, or to do other types of surrogate modeling, for example, approximate your model with a linear model, for example. And why would you use meta features to actually generate these explanations? Well, first of all, because it can lead to better approximation of the model compared to explanations using the original features, but also because it can give you different types of information about the model's behavior, as I showed you some examples of. But thanks for listening. Here I'd like to show you the co-authors of this paper. There's already a working version online, and we're at this moment in the final revision round, so fingers crossed. So yeah, of course it was a group effort and not just me working on this topic. So yeah, that's it from my part, and I'm happy to answer all of your questions or any of your questions.
Thank you, Janu. I found this a very intriguing and interesting discussion. So if people who are listening in still have a question, they can still post it in the comment section. I see that there is only one question, but it's a very long question from a guy called Istvan Heinal. Never heard about him. But he asks, how important were likes on posts of political parties and politicians? So if you would not include those, it would be hard to imagine that liking Radiohead, Starbucks, and so forth, that would have a lot of explanatory power. Because essentially, if you look at the political science literature, we see that those cultural elements don't play that big of a role. So from that perspective, I was quite surprised about your results. And the example you gave, for instance, is if you like Bart de Wever and then you like Het Laatste Nieuws, that's a very strong political statement you make there. And then I can very well imagine that you can explain a lot. But if you're talking about whether you go to Starbucks, whether you like Radiohead or not, it's very difficult to imagine. So can you elaborate a little bit on that?
Yes, of course. Yeah, first of all, I'd like to emphasize that I use this example, like from the paper of Sina, more to conceptually show what we are actually doing here in our paper, and yeah, to show how the rule extraction with these meta features would work. So I'm also not a political scientist or anything. So this, yeah, not sure. Yeah, these insights coming from it, I'm not sure if I can say too much about it. But what I know is that also seen in her work, she compared having a model with all of the Facebook pages, and also having models without any of the political related Facebook pages, and then she compared the predictive performance of this model, and actually models having without these political Facebook pages, actually these models are also very accurate in predicting political interest. So, but yeah, from the explanations that I generated on these models having all the Facebook pages, that's the insights that came out of it, or the explanations that came out of it. So indeed, these pages on political parties or politicians were very predictive in these models. So, but yeah, but it was more to conceptually show you how it works, to have a real data example rather than really argue anything about political insights or political science literature or something.
Okay, thank you for that. I will, before I go over to the question of Lien, and there's also an interesting question from Eric, so I'll be short, but I will definitely read your paper with a lot of interest, because at the end of the day, if you look at how difficult it is to predict voting behavior, we might find some inspiration there. But I'll look out for your paper. So Lien has a question as well, and she says, "I'm interested in how you came by the mapping matrix by means of non-negative matrix factorization." I assume that is. Could you elaborate on that?
Yes, of course. So you have, so yeah, first of all, we experimented with the domain-based meta features. So the not obtained via data-driven approach. But then for the data-driven approaches, we used non-negative matrix factorization as a first approach that we use, because of these non-negative weights that would actually make it more easier to interpret the meta features that we would obtain. And indeed, if we compared it to, for example, singular value decomposition methods, it was way easier to interpret what these meta features actually mean. So we used NMF, but also singular value decomposition to then actually come to this to this mapping matrix that I showed you. Not sure if that answers enough of your.
I'm sure it does, because we're already over time, and I would still like to go to Eric Grunenberg's question. From your perspective, what are challenges that future research in this area should tackle?
Yeah, I really like, that's a good question, thanks. And a very interesting and a very open question, but I think from all the implications that I showed you in the end, I'm personally most interested in these ethical challenges, like, for example, that an algorithm could be very discriminating or indirectly discriminating against people online, or people that are targeted with job postings or housing ads, or pricing algorithms that they actually are indirectly discriminating. And I think that's a really huge challenge nowadays. And I believe that maybe this tool that we propose here, so for example, using these meta features, groups of behavioral features to gain insight into the model, that it can be an extra tool to start probing your model, to start identifying issues within your model. So I think, yeah, these ethical motivations to have interpretability are, I think, the most promising further research area at this moment. But that's maybe more personally, because that's also my research interests. But yeah, I think there are many other future research directions to think about, of course. So, but that's
okay. Thank you. There is, and normally I'm very strict on time, but the interesting questions are pouring in. So the other reason why normally I'm strict on time is that normally after the talk we go and have a beer in the bar. And
that would be great.
That's not the case. I don't have an excuse, so I'll add one other question, and it's actually in two parts. It's from Hildegard van Hove, again, my colleague from my back in the 90s, I guess, a long time ago. And first she makes the remarks and then she asks a question. So first, your example, the algorithm actually increased inequality, and you refer to ethics, which means data scientists should at least be aware of the possible consequences of the systems they build. Okay, that's one remark. But then the question is, do you think that data scientists should also be held responsible for effectively decreasing inequality? That's an intriguing question. I'm interested in what you have to say about this, because this is, let's say, it's an ethical question basically, but nonetheless a very important one. So, what's your idea on this?
Yeah, I think as a data scientist or data scientists, more in the curriculum at first, they need to have more lectures or even courses on this matter, because I think besides the data science part and all the technical stuff, there's also the types of applications that you are deploying these algorithms into, and a lot of issues that can be there as a result. So, but I think they're definitely also responsible for at least avoiding to increase inequality, and I'm not sure responsible for effectively decreasing. So they should not amplify inequality at all using these algorithms. I think that's my opinion. And I think even with using these algorithms, we can hopefully in the future even decrease inequality or have more fair decision making. For example, in HR practices, have a more have recruiting applications that are more fair compared to maybe having humans doing so. Maybe that's a really dream scenario, but I think that's in a nutshell what I think about this matter. But I think data scientists should definitely be aware of all these ethical issues or challenges, and that they should also be lectured more on it within their curricula. So
okay. Thank you very much for these final remarks, and I will think about Hildegard's question myself. It's a very hard one, but we'll see. So thank you again to all the speakers, and my apologies to the audience for running over time, but I think it was for good reasons, because it was an interesting subjects, and we'll see each other again on the 36th Data Science Leuven meetup somewhere in April. Thank you. Bye.